Okay, I guess we can get started. This is Bill Chitty from Berkeley Lab, and this is the Better Buildings Alliance Labs team call, and we're pleased to have Ellen Sweet and Ralph Stewart from Cornell University going to talk about Cornell's Laboratory Ventilation Management Program. And I think this should be an interesting topic for everyone. I think I'll just turn it over to Ellen.
Okay, thank you very much. Thanks for joining, everybody. I'm going to talk about our LVMP, that is a comprehensive lab ventilation management program that is about 2 years old. If you've been with the Better Building Alliance for any length of time, Ralph had actually done a talk for this group a while ago, maybe a year and a half ago, and we've noticed just how far along this program has come. I'm going to talk today about the system as it is structured and how it aligns with stakeholders, because that is a major component of this being successful. I've also written set up the presentation to kind of go hand in hand with the guide to navigating building and fire codes for labs that the folks at Lawrence Berkeley National Lab are working on, because I assume this is going to this is in the works and it's going to be building. Things I'm going to talk about today: the regulatory environment, the goals of the regulations that are involved with lab ventilation, and guidance for general lab ventilation, our program, and then a major component of the program for energy conservation is how we assign general ventilation rates. And then something I've added is a revision to our lab design standard, which it took us about a year to do. It was a pretty major revision, and we brought stakeholders together, so I wanted to talk about that because we're pretty proud of it. So the regulatory expectation for general lab ventilation. Ralph is the chemical hygiene officer. I'm a certified chemical hygiene officer. So we live and breathe the lab standard, which is the OSHA regulation that requires that an employer limit employee exposure to hazardous chemicals that they use in their labs. And this is done by providing directional airflow to control odors, that it says that air should be continuously ventilated. This is not the only regulation that says that. That we are to prevent the increase of air concentrations of toxic substances. And it's because of that statement that Cornell does not bring our lab ventilation down to 2 air exchanges, and that we are very selective on the ones that go down to 3. General ventilation alone should not be relied on for the protection from highly toxic substances released into the lab. That's what the hood is for. So this speaks to the researchers or the teachers' request for fume hoods or some sort of local exhaust during a renovation and new construction process. A lot of times hoods have been put in, and just because it was requested and because that's the best place to control these release of toxic substances. But it's also, as we all are here and we know, uses a lot of energy to provide all that ventilation. And then for the engineering crowd, we can't forget about the building mechanical codes. They can't go below ASHRAE rates. They must design to 1 CFM per cubic foot. For offices, we go as low as 20 CFM per person. That's pretty low, but they do have limitations. So we want to work with them and not compete against those engineers that can only go so low. The lab standard has some guidance, recommends 4 to 12 room air exchange rates. That is normally considered adequate for general ventilation. That's a pretty wide range, but it says that local exhaust systems such as hoods are used for the primary control method. But during the design process, what are you going to do? Put in a lot of exhaust ports and then just close them off? It's very hard to design to what might be going on in the space that'll need local exhaust 20 or 30 or 40 years out. So we try to find some sort of balance there. NFPA 45 says that labs should be continuously ventilated under normal operating conditions, and that hoods should provide containment of hazards and protection for personnel. And that's the NFPA has, in its latest revision, referred to the ANSI 9.5, thankfully, for phase velocities and minimum flow rates for fume hoods, so that we can all use one standard, that we don't have competing expectations. So in writing our program, Ralph and I realized that the ventilation systems being provided to these buildings, you can look at it from three different perspectives that all come together at some point. At the macro scale, we have this building with different uses. Lab spaces, as I said, need to have directional airflow. They're negative to office spaces, and we really don't want them positive in case of some sort of release, because we don't want what happens in the labs to affect other places. And then we also have the air handlers, exhaust fans, variable speed drives, all those building components that have special expertise that, frankly, I don't have. I'm a lab person, but I need those people that do. And that's the design people, that's the operational people, controls technicians, the maintenance personnel that understand those systems that are outside of the room. And then this is where people like Ralph and I come in. You have the mesoscale perspective. It's the room itself, the general ventilation that comes in at some point, exhausted at some point, that needs to move through that room in an effective way. And when it is designed to do that, then you can actually use lower air exchange rates and still remove those releases of fugitive emissions of the chemicals. So this is key when we are looking at even just a single lab renovation or building. We want the room to be set up, the casework to be set up, so that we get the most effective ventilation through the space, so that we have the best chance of reducing the airflow volumes. And then when we also look at the amount of fume hoods in the micro scale, the fume hoods or other local exhaust, then we're looking at the use of the room as a whole, and we can work with the engineers to size the system more appropriately. And everybody working together, we end up with, hopefully, with researchers or the people that are going to be living in these spaces that are more comfortable, that are still safe, that the project is more on budget because we don't have huge air handlers that are going in, and operationally we end up with a better system that is sized more appropriately to the building. But the key thing that we're all looking for is some flexibility of how to make adjustments to these spaces as well moving forward. Okay. So managing these three systems, in order to manage them, they have to interact. We know this. We are taking, at Cornell, a systems approach. We combined two ANSI standards. The ANSI Z10 is the Occupational Health and Safety Management System. It requires defining who the stakeholders are, recognizing who they are and what their roles are and what their responsibilities are, and then using key indicators to track continuous improvement rather than an LVMP, which is a plan that just tells you this is the equipment that you have, this is our design process, and this is how we maintain it. We want to keep up with the new technology that's coming in, and we want to continually make people aware of what their role is. So there's trainings, there's revisions, and so forth. And the use of the labs, and I'll go into the indicators, is a key point for us in laboratory safety. because we're doing inspections and other lab visits, and we want to know that the folks that are using these spaces that we're reducing that engineering control that's supposed to be keeping them safe, that they are actually using it correctly and that they understand what its purpose is. And then the ANSI Z9.5, of course, outlines the institutional specs for general ventilation, storage cabinets, fume hoods, and a variety of other things. Managing systems with multiple priorities associated with a variety of stakeholders is something that the Z10, the ANSI Z10 addresses very well. Because we have two ANSI standards, they're set up very similar, so they have blended together very well. On this campus, we have 1,700 fume hoods. We have about 2,000 labs. There's lots of construction going on all the time. So when you have a variety of systems, a variety of stakeholders, sometimes aligning those is simple, that we can make changes and we can run metrics, we can run measures, and there are simple outcomes. Let me give you an example of that. We have a system in place already for testing our fume hoods every year. According to the Z9.5, they should be within a certain parameters for face velocity. We want 100 feet per minute. If we have fume hoods that go beyond 120, we want to have some change to the program that aligns those, that brings those fume hoods within parameters. And it's a simple process. Well, we hope it's a simple process that we put in a ticket for a fume hood that is above 120 feet per minute. And then we go back next year, that has been repaired, and the fume hood is running at approximately 100 feet per minute. So that is a simple outcome that's predictable. But in a system such as this, it's very complex also. A change that we make in the program results in, it's like the snowball effect. There's a variety of outcomes. Some of them are predictable and some of them are not. So that's what makes this program very complex. Especially when you have all of these stakeholders involved. Managing these systems requires flexibility in practice. We really want to have flexibility in how we design these labs with certain parameters in place that aligns the designers, even the inside ones and the outside design folks that really may not understand our expectations. But to have some flexibility in that system so that we can work with it once the building or the lab has been renovated, constructed. Laboratory ventilation managers face competing priorities. This institution, we teach and do research of science. We have to keep everybody safe, but the sustainability of doing things is very much in question. It's becoming increasingly expensive to do science and to teach science. So that's why a program like this that is continuously improving is very important, and we have the support from the top all the way to the bottom. Sustainability is becoming increasingly important around the country and on this campus as well.